So overall, exam 2 went pretty well. I think the average picked up by like 6 or 7 points. So probably did better on exam 2, average speaking, than we did on exam 1. We left off right in the middle of talking about what makes a reaction tick. So this is going to feel a little stale because we haven't been talking about this for the last couple of days. But I believe we left off with delta G, that reaction or that equation. So I want to just pick back up there. We're trying to decipher what allows a reaction to occur, right? So are we going from energetically high materials or energetically low materials to products that are high or low? I don't think I put this up. Maybe I did. Does that look familiar to anybody? Yeah, okay. So we had said that the free energy change, this is going to be a little bit of a review just to get us back into it. The standard, so that knot up here is the standard free energy change. Is going to be dependent on the change in the heat. So delta H is the enthalpy change. Minus T, which is temperature. Delta S, which is the change in entropy. Oh yeah, I talked about this because I did my little dumb marker thing, right? Right. Okay, what I want to do is think about each one of these terms, delta H and delta S, and what impact they're going to have on delta G. Remember, if the reaction is going to go forward, if we're going to turn reactants into products, we want delta G to be negative. We want the system to give off energy. We want the reactants to be up here and the products to be down here, and they're going to fall down. So when they fall down, energy is given off into the system. Real briefly, I had a conversation with my son about this over the weekend because it was cold and we made a fire in our fireplace. And so at like 8 o'clock in the morning on Saturday, he was like, "Dad, why is fire hot?" And I was like, okay, well, so the energy in the wood is high and the carbon dioxide and water coming off the wood is low energy. So the energy has to go somewhere. So it's into the environment. And he just stared at me like, because he's 4, and that was a dumb explanation. So then I was like, okay, no. So the energy, the wood is really excited. And when we turn it into not wood, it's not as excited. So all its energy comes out at us. And that's why it feels hot. He was like, okay, I'm down. So I was telling him about delta G. Let's think about these terms as far as giving off heat or taking in heat, becoming more disordered or more ordered. If we want delta G to be negative, we want delta H to be negative. Because a negative delta H, there's no term in front of this, is going to make delta G negative. The more negative delta H is, the more negative delta G will be. If we have a negative delta H, that is called let me put this in red. That is called exothermic. And that is favorable for turning reactants into products. The opposite is true if I have a positive delta H. That would be an endothermic reaction. That would not be favorable. For turning reactants into products. Very slightly close the door. So if we want that reaction to go forward, we want the system to give off heat. We need to watch how much heat's actually being given off there, because a large amount of heat being given off is what we call an explosion, right? So when TNT goes, what's happening is the TNT has a very negative delta H. There's a lot of heat released from that. The heat and pressure is what causes the explosion. So that should make some sense, right? That delta H mirrors delta G. If delta H is negative, delta G is negative. No deal. No big deal there. How about delta S? Delta S is a little bit different because there's a negative sign in front of it. So that means we are going to think about this in opposite terms. A negative delta S is going to be multiplied by a negative T. A negative times a negative turns into a positive. So that's a problem for us. If we want delta G to be negative, we need delta S to not be negative as well, because there's this minus sign here. So a negative delta S doesn't have a fancy name. It is just unfavorable. For turning reactants into products. How can you have a negative delta S? One way to think about it is we could be adding molecules together. So if I had A plus B, this is an example, A plus B turns into C, that system is reducing the entropy because I have two molecules over here turning into one molecule over here. And so I'm inherently constraining that system because I had two molecules that could run around like crazy. And I said, no, you can't run around like crazy anymore. Now you're linked in a product. Let's see. Nature doesn't like that. Nature wants things to spread out a lot more. Nature would love for entropy to increase. A positive delta S is favorable for turning reactants into products. An example of that would be if you took A and turned it into B plus C. Here I'm taking a molecule and I'm breaking it apart to form two other molecules. One molecule is forming two. So I've increased the randomness, I've increased the disorder, I've increased the entropy in that example. And if you can remember this equation, delta G equals delta H minus T delta S, then you can just work this out mathematically. So for those of you who are big math people, unclear about you generally speaking, but you probably will like this, where you can say, I want this thing to be negative, so this thing better be negative. I want this thing to be negative, so this thing better be positive, because a positive number is going to get multiplied by a negative number. If you want delta G to be negative, we want delta S to be positive. Do we see how that flows from the equation? Yeah, I know this is not the most like enthralling piece of organic chemistry that we talked about. So, this is going to get a little squished in here, but let's try and put it in here. Delta G equals delta H minus T delta S. If delta H is negative and delta S is positive, the sign of delta G is going to always be what? Negative. Are those reactions spontaneous? Do they flow naturally from reactants to products? Yes. This is be a spontaneous reaction. Spontaneous means reactants turn into products. You don't have to push them. You just mix the two together and the reaction takes place without intervention. What about if delta H is positive and delta S is negative? What is the sign of delta G always going to be? Positive. These reactions will not occur or are called non-spontaneous. Which basically means, and let me just abbreviate that because it's getting too crowded in there. It basically means if your job is to run that reaction, you're going to be having a bad day. You're going to have to heat it up and add catalysts and do all sorts of interventions to get your reaction to go forward. It is not favorable to turn reactants into products under these conditions. What about if delta H is negative and delta S is negative? Or delta H is positive and delta S is positive. What's the sign of delta G in both of those cases? Sometimes. It depends on what? Temperature. So in this case, both of these reactions are temperature dependent. In this case, I have a favorable delta H term and a disfavorable delta T term, delta S term. So what I'm going to do is I'm going to cool this reaction down, because as my temperature number gets lower and lower, my unfavorable delta S factor gets smaller and smaller. So this is kind of weird. You would run one of these reactions and it wouldn't work until you put it on ice. And once it got cold enough, then the reaction would run. Those are very strange conditions. Typically, that's not how this would normally work. Normally, that is this kind of situation where you have a not favorable delta H, but a favorable delta S. Sorry, guys. This is probably going to be an ongoing thing. Yeah, they're having like a big conference here on Wednesday. So, you know, if it's very loud by that back wall, you could come on down. See? All right, so delta H is no good for me here. It's not doing me any favors. Delta T or delta S is. So I'm going to heat that reaction up. And I'm going to have delta S drive, because this is negative, drive this delta G to be negative. So in this top one, I would cool the reaction down to make it spontaneous. In the bottom one, I would heat the reaction up to make it spontaneous. And in both cases, I wouldn't be very loud in the hallway. We are going to be good stewards. There's a number of officials back there that we will give some latitude with. If we need to go talk to them, I will go talk to them. We good so far? Okay. Are we super distracted? Do I need to go talk to them? Okay. This is good, like focusing on like a thing. Any questions about delta G, delta H, or delta S? Does anyone have any idea what I'm talking about up here? The last two. Okay. There's some information. Let's talk about what makes these factors tick. It takes energy to break bonds, and we get energy back when we make new bonds. And this is where I really lost my son, because I was like, I almost said the word cellulose to him, because he was like, why is fire hot? And I was trying to get across to him that when cellulose breaks apart, it turns into carbon dioxide and water. Cellulose is high energy, carbon dioxide and water are low energy. So we go from high energy to low energy and heat comes off. But you have to put in energy to break apart a bond. Bonds are not like glow sticks. You don't just crack a bond open and energy pours out. To break a bond, you have to put energy into it. It's when we form bonds on the other side that energy comes back out. Fire is hot because fire produces water and carbon dioxide. Fire is not hot because gasoline burns very easily. It takes energy to break apart gasoline. It's the products you make on the other side. Try explaining that to a 4-year-old. So let's talk about that energy called bond dissociation energy. Or capital D. If I have, and we'll use hydrogen because it's easiest. If I have a hydrogen molecule and I want to break it apart into 2 hydrogen radicals, how would I show that with arrows? I like that everybody's like doing it in real time. This is where we need like some tablets. One is going to go this way, double or single-headed arrow. Single. And then over this way, double or single. Single. 5 points, nailed it. This is a radical reaction. Which step of the radical process is this? Initiation, 10 points for Gryffindor. If I was going to break this molecule apart, I have to put in heat as a reactant. And so you can almost like write it this way. For hydrogen, I would have to add in 436 kilojoules per mole. Kilojoules is an amount of energy. Mole is amount of stuff. So a mole is a large number, 6.02 times 10 to the 23rd, but it's just a way of counting number of hydrogen atoms. I would have to put in that much energy to convince 6.02 times 10 to the 23rd molecules of hydrogen to break apart and become hydrogen atoms. What this should tell you is hydrogen doesn't want to be radicals. Hydrogen wants to be hydrogen molecule. I have to add energy to a hydrogen molecule to get it to separate out into these two species. And so we could write for this, the bond dissociation energy for this reaction is 436 kilojoules per mole. I'm writing it here like it's a reactant. I'm writing it here as just a feature of life. That's a number you'd look up. I don't need you to know any of these bond dissociation energies. I need you to know how to use them. The important part here is we add energy to break bonds. We can also refer to the bond energy from a formation. We can also use something called the delta H of formation. How do I want to write this? Delta H of formation, which is often just abbreviated as delta H F, also refers to the energy produced when a bond is formed. You know, something I should check on is that I think they're wanting to use this classroom on Wednesday, so I can probably make sure that we're not going to be in the middle of a police conference on Wednesday, because I have a feeling that's what's about to happen. So everybody watch their emails about where we're going to be on Wednesday. So if I wanted to refer to delta H of formation, that's the opposite, right? So I'm taking an H radical and an H radical, and I'm going to form an H molecule here. How do I show arrows for that? One goes here, one goes there, form a bond. Here I would show the delta H of formation is negative, negative 436 kilojoules per mole. Well, I just set up here the bond dissociation energy was positive 436 kilojoules per mole. Down here, the heat of formation is negative 436 kilojoules per mole. Bree, I'm going to answer your question, but before that, oh, okay, I'm going to ask you, why? What the heck? What's going on with that?
That's what I was going to ask you, because the bond is together, when it's positive and it's broken, and then it's negative.
We are adding energy to the system here. If I had a mole of hydrogen in front of me, I would have to pour in 436 kilojoules of energy to get that molecule, that mole to break apart. I am adding energy to it. So it is a positive here. If I took a mole of hydrogen radicals and let them combine, 436 kilojoules of energy would come out as a reactant. So I could almost write it over here like two radicals form, and then I also produce 430. I'm not going to write it here because it's going to be confusing, but if I wrote 436 kilojoules per mole over here, it's a product of that reaction. Essentially, if I took hydrogen radicals and let them combine in front of my face, I would die because they would explode. They would form hydrogen molecules, give off a ton of energy, set themselves on fire, and then would explode. So we refer to the heat of formation as a negative number because you make energy You produce energy when a bond is formed. Add energy to break bonds, make energy or produce energy when bonds are formed. That make sense? Okay. We have been talking about all these things that make up, that describe how a reaction proceeds. And I've been deeply uncomfortable with all this because there's like a lot of math in there, and I'm not a mathy kind of person, and this isn't a mathy kind of subject. Organic chemistry often will draw pictures to depict mathematical operations, and so I want to show you another way of doing that with something called a reaction coordinate diagram. Energy diagrams have many different features to them. First one we'll talk about are transition states. So I have shown you this reaction a bunch of times at this point. So what is the first step? I'm going to draw a mechanism for this. What's the first step I'm going to do here? Loud and proud, Sakina.
That's what the top one.
Yeah, word. Double single-headed arrow. Shown up. Now what? Double-headed arrow still, right? So I'm showing you a polar mechanism here. That's going to make a carbocation. So I'll put the hydrogen on one side. The Br minus over there. Positive charge went here. See, they left. I gave them a mean stare. I was like, you get out of here. They didn't. They're done. The Br minus then is going to attack the positive charge. That arrow is too far away. And then it's going to leave us with our final product. What I want to do is map out this reaction on a plot that shows a difference in energy and follows the reaction progress, or you'll also see this called the reaction coordinate. Low energy, more stable. High energy, less stable. Left-hand side is going to be reactants. Right-hand side is going to be products. So as we go from left to right, we're going to walk through the reaction and we're going to talk about the energy changes that occur as we do that. So let's start over here with our reactants. How do we feel about these reactants compared to, say, the intermediates? Are they less stable or more stable? Guys over here, more stable or less stable than guys over here? More stable. So what I'm going to do is just draw a line here, and that line is going to represent my reactants. I'm going to just group them together and say the average energy of those two is this line. When the ethene reacts with HBr and forms these two intermediates, am I going up in energy or down in energy? Up quite a bit. Why? Because we're breaking a bond here. We did form a bond there, but we broke a bond there. But why else? What about them? They're present, right? So these things were neutral. So we went to charged species. That's not great. But we did something like where if you saw this, you'd clutch your pearls and go, oh. No. Look at the carbon. Oh, I can't watch. It doesn't have an octet. We've broken the octet rule on the carbon. Oh. So the carbon doesn't have an octet. It is very high in energy, right? Very unstable. When the bromine attacks that carbon, we get to a product that is more or less stable than this stuff. Is the product more stable or less stable than where we came from? More stable, right? We took care of that mean old lack of octet carbon and we made everybody neutral. So we're going to fall back down, and it wouldn't be immediately obvious to you all about how far to fall back down here. But if you look what we did, we broke a carbon-carbon pi bond and made 2 new carbon sigma bonds. So what do you think about that? We broke a pi bond and we made 2 new carbon sigma bonds. Is that good bond math or bad bond math? Good. We broke a relatively weak bond. Pi bonds are weaker than sigma bonds. And we made 2 new sigma bonds. Now I broke a sigma bond over here too, but it's pretty weak. So overall, this reaction is going to be exergonic because my products are going to be lower in energy than my reactants. So if I could pretend to draw a straight line here, that's delta G. The difference in energy between the reactants and the products. The products are lower in energy, so my delta G here is negative. I fell in energy from the reactants to the products. Now, I went over an intermediate that is very much higher, but at the end of the day, I started up here and I went down here, exergonic. So the firewood up here, carbon dioxide and water down here, energy went off. Where did the energy go? I warmed up my hands and I felt real cozy. I put a sweater on. Anybody else put a sweater on this weekend? Sweater weather? It was great. You got to enjoy that because maybe you were near a fire and got to experience this exergonic reaction. That doesn't make any sense at all. I'm going to move away from that. The reactants turn into the products following a curve that looks like this. So this represents, this line here represents my intermediate. Come back to that. But notice that I drew a line that kind of bumps up over top of the intermediates before it gets down here. What's the top of this hill called? The transition state, which does involve the activation energy. I like that you guys are like, oh, Jin Kim, here it comes. You're right. The energy that it takes to go from the reactant, maybe not too many dotted lines. If every line is dotted, no line is dotted. The energy to go from the reactants to the transition state is called the energy of activation, or the newfangled way of writing that is the delta G dagger. That dagger means transition state. When we go between species, there's always going to be a transition state. And I'll draw this out for you exclusively in a little bit, but the reason there's a transition state, easy for me to say, is that I haven't quite settled any of the accounting here. I'm breaking bonds and forming bonds, but everything's kind of in between. So when I go from an intermediate to a product, there's going to be another transition state, and it's going to flow down here. It's going to have its own activation barrier that'll be there, but you notice that that activation barrier, this E sub A is very small. So we don't call that the energy of activation, because if I have enough energy to get over this hump, I have enough energy to get over that hump. Is anybody a roller coaster fan in here? A couple of us? All right, so if you are a roller coaster fan, as you're going up the roller coaster, this is the point when you're like, hey, a fun thing's about to happen. This is going to be great. If you're not a roller coaster fan, this is the point where you're like, I'm about to die. And then you get up here to the top and you're like, oh, hey, this isn't so bad. And you go over like a little hump and then you die, right? It's like kind of slow at first and then everything takes off from there. Roller coasters, you may or may not know this, are not powered. There's no motors to them. They literally just fall, right? So you are falling in a roller coaster. It works because you go tick, 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 gonna die, tick, 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 tick. You get up here, it puts all the energy in you need to complete the rest of that coaster, and then it lets you go. And you go all the way down to products. So this is the energy we have to put in to get you to complete the coaster. This is the energy we have to put in to get you to complete the reaction as well. So while that is a transition state, we don't even typically refer to it that way. Or why that is an energy of activation. That transition state is not as important to us as the other ones. So we would call this transition state 1 and transition state 2. Let me dive into this a little bit more, but before I do that, this is the first time maybe you've seen a reaction coordinate diagram. Do you see the utility of this? How we're mapping out the math of delta G and energy changes between reactants, intermediates, and products? There will always be a reaction coordinate diagram for every mechanism you draw. I'm not always going to have you draw it, but for every structure that we draw, there's an energy change associated with it, and we can map them out here to explain why a reaction occurs the way that it does. And this map prevents us from having to do the math every single time. We can just say, oh, the reactants were higher than the products, so that must be a negative delta G. Let me think about why that might be that way. We'll cover a lot more of these, but let me focus in. Sorry, I asked you if you had questions, and I just talked right over that. Does anyone have any questions? Okay. Transition states. He's so weird. Guys, I don't know. I'm not sure. Transition states are high energy structures between reactants and products. Importantly, they are not isolable. That's probably not a word you've ever used in your life. Isolable or not non-isolable means you can't put it in a bottle. I can't go, hey, here's a transition state I made for you. Take it home and tell me about it. Transition states are theoretical places that molecules go to when they are forming bonds. We draw them like this. So we don't typically draw them, but when we draw them like this. I said that first step of this reaction is for HBr to react with a pi bond. The pi bond is going to break and form a new bond to that hydrogen. The HBr bond is going to break and push the electrons onto the bromine. A transition state is typically drawn in brackets, and we use dotted lines to show the bonds that are breaking and forming. So I am breaking a pi bond. This line shows that pi bond going away. So I'm going to draw the pi bond in a dotted line. I am forming a new carbon-hydrogen bond. So I'm going to draw a dotted line up here to the hydrogen. I am breaking a hydrogen-bromine bond. So I'm going to draw a dotted line there. But I'm going to put all those lines in together, even though if I drew solid lines, I'd be breaking the octet rule here, right? Because the pi bond is breaking as the sigma bond here is forming, as that sigma bond is breaking. I'm going to let you all know that it is a transition state by drawing a box and putting that little dagger here. And the way you read this is, I have a pi bond breaking. I have a sigma bond form. and a sigma bond break. And that's why these things are so high energy. Because I'm losing the stability of all my bonds, but I haven't made any new bonds back officially. So it's this like in between time. If this was like a no, I'm not going to use that because we got some serious shit, stuff going on in the world right now. If you were giving someone a bag of money, right? I haven't officially lost my money yet. You haven't officially gained the money. It's like me in the process of trying to give it to you. It's kind of in this in-between space. It's the most fragile when you're handing something over. The other way to talk about this is pretty stupid, but we'll see if it works. If I'm in a reaction coordinate diagram here, right? So energy is this way, reaction progress is this way. I'm a reactant. Here is the intermediate. Here is the product. You can isolate me here and say, Dr. Green, stop, be a reactant. I'm here. Right? I could come over here and you can say, Dr. Green, stop, be an intermediate. I'm high energy, but I could be here for a little while. Similarly, I could stop at the product as well. The transition state would be me going, okay, I'm going to turn into the intermediate. Ready? Transition state. Right? You can't freeze me in the middle and it would look really super awkward because I'd be going like a penguin. Right? But it's me in the process of turning from a reactant into a product. You can't isolate me there, but you know that it happened because you probably, like, if you filter back in your head, you're like, that was really dumb. But I was here for a while, I landed over here, I stayed in those two areas, and I was briefly in between. That's a transition state. As many of you mentioned earlier, the stability of the transition state is important because it controls the activation energy. Unstable transition states are really high energy, and that's the activation barrier we have to get over. I'll write this out. Controls the energy of activation. Which is E sub A or delta G dagger. They mean the same thing. Let me just show you two examples here. Remember, when you draw a reaction coordinate diagram, you are drawing a graph. You want to really annoy a scientist, draw a graph and don't label your axes. Label them both, right? Energy, reaction progress, or coordinate. If I go from a reactant to an intermediate, and I go over a unstable transition state, it would be like this. And if I went over a, making the same level here, reactant, that turned into similar level intermediate here, but went over a more stable transition state, this reaction would be slow, relatively. This reaction would be fast, relatively. My transition state is controlling the difference there. If I go through a really messy transition state that requires a lot of atoms to move around and get into really uncomfortable orientations or electronic structures, that reaction is going to require a bigger hill. That's going to require more heat to get this thing to turn into the intermediate. More stable transition states, lower activation barriers, faster reactions. That makes sense, Gen Chem students? Does everybody remember this from Gen Chem? Or remember being tortured by it in Gen Chem at least? Okay. That's transition states. I don't know why I can't say that word today. Let's talk about the other thing that we've mentioned in here, which is intermediates. They are structures that transiently exist during reaction. They technically can be isolated. Although most of the time what we mean by that is they can be detected. So we can use some sort of method to capture or see that an intermediate formed. You often won't see an intermediate put into a bottle though. Right? So I can put a reactant in a bottle. I can go to the shelf and get a reactant. I can make a product, put it in a bottle and give it to you. Intermediates are typically too high energy. They're too reactive for me to put it in a bottle. If I put an intermediate in a bottle, I normally have to keep it very, very cold and isolated from atmosphere and a whole bunch of other measures to make sure it doesn't react with anything else. They are said to exist in a local energy minima. I did not know what that meant when my calculus professor, which is the class that I failed, was trying to tell me. He was a sweet old man and he tried really hard and I just wasn't there for it at all. He was like, hey, Nathan, I've got some fun things to tell you about calculus. And I was like, I hate this class, but you're a sweet old man. And then I failed. But he was trying to tell me about if you picture yourself being on a graph. You know, if you have a physics professor or a calculus professor is telling you to envision you're on a graph, you've got a good calculus professor. Right? Because the rest of them will just be like, deal with it, it's a graph. So here I am with my top hat, very excited. In the intermediate, when I look to my left, I see a hill. When I look to my right, I see a hill. I am in a local energy minima. It's not the lowest energy that this reaction can be at, but I am sitting in this little well. So the roller coaster example is when we go up here and we go over this peak, the coaster slows down a little bit right here. A lot of roller coasters do this to you to give you a relative sense of the speed you're about to go at. If you just went up and then fell, you'd only get the one drop. But if you go, then drop, you get a little bit of motion and then a lot of motion. And it makes the motion feel a lot more intense. So many roller coasters will have local energy minima. So you slow down a little bit before you go over the other hill here. The energy well that this is in allows the intermediate to stop there for just a second. So again, if I was going to act out going from a reactant to an intermediate to a product, which ironically spells rest in peace. Reactant sitting here, very stable, right? I'm going to hop over to the intermediate and then to the product. So can't isolate, sit here for a bit, now product. I was there for a little bit. You could see me be there. You could technically say, hey, for a minute he was there, but I just popped over to the other space pretty quickly. I can occupy this space really well as a product. I jumped too far. I can occupy the reactant really well. The intermediate is this like hot potato situation that I don't want to be in for very long. And remember that what I'm doing is hopping over those transition states along the way. That's the intermediate. You guys look generally pretty bored, so I'm going to assume that you know what I'm talking about and I don't need to beat this to death or hop around over here anymore. Is that right? Or is this generally just boring? I think, what's that? Processing. All right. And it's a little bit boring too. I would have you all get up and act out the transition state intermediate process. So you all just hop along. There's some good homework about how to draw these things out. But what we're going to do is we're going to draw reaction coordinate diagrams to map out reactions that we're running. Yeah. It'll be good.
percentage of the, how many kilograms is that?
I'm not going to have you memorize, I'm not going to have you do this from a numerical standpoint. I want you to qualitatively be able to tell me that this process going from a reactant to an intermediate is uphill in energy. This takes energy to go here. To go from this intermediate to that product is downhill in energy. Energy is given back off. And that we can identify the distance between these two here as the delta G. So this reaction is exergonic. It gives off energy. It would be spontaneous. Would the KEQ of this reaction be greater or less than 1? Greater than 1, because the reactants spontaneously turn into products. Now, that's not the world's biggest delta G, so I'd say it's probably a little bit bigger than 1. The bigger the delta G gets, the higher KEQ gets, because there's more motivation to turn things into products. We're going to use these reaction coordinate diagrams to talk about why reactions occur. So for now, I just need you to know about the facets of what makes a reaction coordinate diagram a reaction coordinate diagram. Because they can be really handy when we are talking about, I'm just going to draw this on a big slide here. They can be really handy when we are talking about things like catalysis. There's no reason for this to be this big, but it's my last topic, so what the heck, why not? Let's pretend that I have a reactant that's not going to make an intermediate. It's just going to go straight to products. If I run this reaction in the lab, it goes over this big hill and produces a product. So this is my uncatalyzed reaction. But I did a bunch of research and I was like, wait a minute, if I add like aluminum to this, the aluminum acts like a catalyst. So I can turn that same reactant into that same product, but I'm going to go over a slightly lower barrier. This would be a lab catalyzed reaction. I have decreased the transition state energy here, so I don't have to put as much energy to turn a reactant into a product. I added some helper molecule that allows the reaction to proceed by lowering the activation barrier. Our bodies do this in a really ingenious way. In our bodies, we do catalysis, but we use certain proteins called enzymes. So an enzyme catalyzed reaction does something I cannot do in the lab. Glycolysis is a great example of an enzyme catalyzed reaction. To turn glucose into 3 molecules of ATP is a miracle. And I don't mean that in like in necessarily a religious way, just in a like, that's insane. If you look at the structure of ATP and the structure of glucose, they look nothing alike at all. If you said, Nathan, here's a pound of glucose, can you turn it into ATP? I'd say, please go away. I have no idea what you're doing. But my body can do it very easily. If I eat candy, I can turn it into ATP real fast. The way that we do it biologically is we break these things down into several intermediates. So we say we're going to go from glucose to a slightly higher molecule, to a slightly higher molecule, to a slightly higher molecule. And those each have their own tiny little transition states. And eventually we get to a high enough energy molecule that can then fall down the rest of the way and turn into, in this case, ATP. But all of our biological processes occur this way. That's why we can do some really insane chemistry at body temperature. Do you know how much I would have to heat up glucose to turn it into ATP? I would melt if my body was the reactor I was trying to use to do that in the lab. I would have to put in insane amounts of energy to make that happen. But my body doesn't have to because it breaks it apart one bond at a time because it has this protein machine that allows that to occur. Which is why so much of human health and sickness is involves proteins breaking down. If a protein in my body isn't present or it's not functioning correctly, I can't break down glucose. Or for some of you, got lots of people in the family this way, they either don't have lactase or they have some lactase enzymes, but they don't work very well. So if they drink cow's milk, they get lactose, another sugar in their bodies that we don't have a protein machine to break down, and that really messes with their GI tract. This is a way of showing how our enzymes catalyze reactions in our bodies. You're all very fascinated by that, I can tell. I'm going to leave this subject behind, and on Wednesday, we're going to talk about alkenes. If you want to practice some of this stuff, we have Action Center in 10 minutes. See you then.